So as I teased you last time, we are going to do some other failure criteria for fatigue this time. And those two criterion that we are going to look at are the Gerber criteria and the ASME Elliptic criteria. And so I figured by way of introduction to this, this topic, what I would do is give you a little bit of experimental data. The only format they had this data listed in the book was this format that you see over here on the left. I kind of wish it wasn't in exactly that format, but this is how it is, and so I have to give a little bit of background. What they are doing for both of these axes is they are normalizing those axes to the strength values that are associated with those axes. So down here you have mid-range stress. We talked about mid-range stress last time. The value of like stress that occurs in a part that you should compare against an ultimate strength, that would be like the mid-range strength. You compare the mid-range stress to the ultimate strength, and that kind of gives you an idea of how close you are to sort of the static portion of possibly failing your part. And then you compare the alternating portion of your stress to the endurance limit, because that tells you how far you are into the idea that you could fail your part by cycling the load too large a number of times. Okay, so that's kind of the two axes that we're dealing with there, and they are normalizing these two axes by dividing sort of the stress values by the strength values, which is why they wind up being from 0 to 1 and from 0 to 1. All right, and you'll notice there that this black line that passes down through the middle of, not really through the middle of the data, but that passes kind of by the data, that is the Goodman line that we looked at last time. It's a straight line that is drawn essentially from the endurance limit value down to the ultimate strength value. All right, and what you see here is that most of the data lies above that, that line. So in other words, the Goodman line doesn't actually do the best job of describing sort of the mean of what the phenomena actually is. Okay, and so that's where these two categories of failure criteria come in and are useful to us, is they do a little bit better job of creating a line that describes the mean of what the possibilities tend to be. Okay, and so the first one of these that I'll mention is the Gerber line. And the Gerber line is actually a parabola. And if you were to draw that parabola on here, it would basically look something like this. Okay, I may not have drawn it perfectly, but there's something of a parabola that gets fit through that data. And this is actually the one that, by most people's estimation, does the best job of describing the mean of what the experimental data tends to indicate. Okay, so this is the Gerber line, the Gerber parabola. And what you see over on this other chart is a more common way to express that. It's where you are not normalizing the two axes. You're just showing that parabola extending down from the endurance limit down to the ultimate strength. So from here down to here. Okay? And this is a good criteria for us to use. The one thing about it, though, that you will notice is that there's this other line, this Langer line, that comes down through here. Okay, the Langer line is where you would have first cycle yielding happening before you actually got to the point that it would have like fatigue type of a failure that might occur. Okay, so this is the yield line. And what you notice there is that especially if the load line has a very shallow slope, like if you had a load line that was going out this way, for instance, okay, you end up with a large disparity between where the Gerber line says that there would be failure and where the Langer line says that there would be failure. In other words, there would be yielding quite a bit before your Gerber line would predict that there would be some kind of a failure. You see how that works? Okay, so what we do as kind of a response to that, or what someone did as a response to that, was they created a different curve that went through this. And you see this other curve on here. It's labeled ASME Elliptic. It's this one that comes down like this. Okay, And what it is it's an ellipse that is fit to the data instead of the Gerber line, which is a parabola. It's an ellipse that gets fit to the experimental data. And it's set up so that it dies into the yielding strength instead of into the ultimate strength. Okay? And what's interesting about that is this one's a little bit harder to draw on this figure, but it more or less mirrors for most of the way. It mirrors what's going on with the Gerber line, but then it falls off something like this. Okay? And it hits down here where, ostensibly there would be a yielding strength value, and that won't be necessarily the exact same ratio for every type of material, but down there's going to be some yielding strength value where the ASME elliptic line or curve meets that other spot. The advantage of the ASME elliptic curve primarily is that it has built into it some level of accounting for the idea that you could have first cycle yielding. Now here's the problem. It doesn't do it perfectly, right? So you actually look at this. The yellow here is what predicts that you're going to have first cycle yielding, right? The red here is where your ASME elliptic criterion is going to predict failure. And you see the fact that it is outside of the yellow line means that it is, in some cases, not going to predict failure at a point when you really would have, when you really would have first cycle yielding. What you got? So the Langer line it would be difficult for us to plot on there because this one, the one on the left, is normalized to endurance strength, and we don't have a good relationship that always works between endurance strength and yielding strength. And if you'll notice here, this line is drawn from yielding strength down to yielding strength, and so that would be a difficult line for me to try to draw accurately on there. I mean, what I could do, I can say very, very generally, it would probably be something kind of like this, right? Because all we're doing, these are the same things, it's just the scales are normalized relative to certain strength values, right? The figure I have on the left is the same as the figure on the right, the only difference being that on the left we have the scales normalized to strength values, whereas on the right they are just in absolute strength numbers. Does that make sense? So anyway. All right, so, yeah.
You said the ASME line predicts, it accounts for some degree of first cycle yielding?
Yeah, so built into it, what you notice there is like for this blue line right here that I drew on there, you're going to have very much less disparity between what your Langer line predicts as when yielding occurs or when failure occurs versus the ASME elliptic line, which means that your ASME elliptic is getting closer to intrinsically accounting for the idea of first cycle yielding being a failure possibility. Okay? But all of this little area right in here, okay, this is the problem. See that little area right in there? The problem there is that on this load line, as you get more and more severe loading, you get further and further out on this load line, and you could end up in a spot like right there.
What happens right there?
Right there, you are having first cycle yielding. You should predict that you have first cycle yielding because you're outside of the Langer line, but you're inside of the ASME elliptic line, which means that ASME elliptic is not yet predicting failure. Right?
So you could have this first cycle yielding, but you're not having failure.
What you're having is you will have first cycle yielding if you go outside of that Langer line, but you're inside of the ASME elliptic line, which means that it's predicting or it's saying that your factor of safety is going to be greater than 1.
Okay.
Right? Now, it could be argued that because we are not taking any of these curves to be absolutely deterministic, and these are sort of some ranges where we start to get concerned, right? It could be argued there that you can use the ASME elliptic, and as long as you are planning on using some factors of safety that are, relatively decent ones, it might not make much of a difference. But it's one of those things you have to be aware that even for ASME elliptic, it might be important for you to evaluate the issue of first cycle yielding. Okay? All right, so that's kind of what we're working with here, and what we're going to do is a problem where we evaluate factors of safety using these two criteria instead of Goodman like we used last time. Sound good? All right. So here's our problem that we're going to work. We haven't done a torsional problem yet, so this will be a chance for us to work a problem that is set up in torsion. So this problem has a roller, and this roller is set up so that, ostensibly anyway, the roller is rolling over some sort of maybe a part that's on a conveyor. Think of it that way. Okay, so we have these little parts on a conveyor that are moving with a velocity to the right, and as they move that velocity to the right, this roller will actually roll over the top of them, and as it does that, it will cause this torsion bar to have to twist. Okay? Now, what it says up here, 12 degrees of pre-displacement. What do you think that means? So I'll kind of describe what that means. That means that in the position the roller is shown right now, there is already 12 degrees of displacement, of twist, that is put into that torsion bar. Okay? And by the way, torsion bars are a very common way to achieve spring action. All right? This is not uncommon to see there be a piece that is twisted, and that's how you are going to store some sort of mechanical energy in a spring type of an action. And so that's what's going on here, is we're using this torsion bar as a spring to create load that is pushed down from the roller onto these parts as they roll by.
So it's already 12 degrees angle.
Yeah, so you think about if I was to take the whole conveyor out of the way, what this thing would do is it would spring down to a location 12.5 degrees down from here, and this is where the roller would be if I was to let it go to where it wanted to be. But the conveyor is in place and keeping that from happening, so there's always a load being put on the bottom of this roller, even when it's not rolling over the top of the parts. Okay? All right, so that's going on. We're given the dimensions there of the torsion bar. We're given the length of it. We're given a couple of diameters. Of course, the diameter there on the end is 0.6 inches. The diameter in the middle is 0.5 inches. It's got a machined surface on it. We want 90% reliability. We're also given that the little radius values where the diameter transitions from one size to another. We're given what those values are. We are also given that the torsion bar is made out of a particular kind of material. That material is 1095 steel, quenched and tempered at 1200 degrees Fahrenheit. And again, so that we can save a little bit of time, I'm not going to spend time looking that material up. I already did it. So out of table A21, we are given that the ultimate strength for that material is 130 KSI, and the yielding strength for that material is 80 KSI. Okay? And here's what we want. This is the situation. Oh, and I meant to mention this too. The height of the little blocks of material that are being rolled over with this thing, those are 1/8 of an inch tall. Okay? And the length of the arm is 2.5 inches long. All right? So what we want to do with this is, for this situation, we want to evaluate factors of safety using the ASME elliptic criterion as well as the Gerber criterion. And we want to do this as factors of safety against fatigue, assuming we want infinite life. All right? We clear on what we're going for here? Okay, so what are our steps? Okay, we probably need to get some Marin factors to adjust our, fully adjusted or fully corrected endurance limit. So I agree that that's one of the things that we're going to need to do. What else are we going to do? Okay, we'll need to find our maximum and minimum torsional stress that we have here, the shearing stress induced due to torsion. We have to do that, and in order to get the max and min that we really want, what else do we need? We need a stress concentration, right? We need a fatigue stress concentration factor. That's another factor that we will need before we get this problem completed. What else do we need to do after we get all of those things taken care of? We need to actually apply the, the failure criteria equations in order to figure out what these factors of safety really are. Okay? And I think one of the things that we should also do, and it's listed up here, we will also check for first cycle yielding. All right? We ready? Where should we start? Okay. Well, I'll tell you where I like to start, and there's a reason why I like to start at this particular spot. I like to start with my stress concentration factors. Okay. The reason I like to start with that is I will need those to get my maximum stresses, and so I like to kind of work it in that flow because it's something that I will need before I actually come up with my maximum and minimum stresses. So I usually start there. So let's start with our stress concentration. Okay. We have stress concentrated because the diameter of this torsion bar changes going from the 0.6 inch diameter down to the 0.5 inch diameter. And so what we need to do is find, first of all, the chart that allows us to come up with our theoretical stress concentration factor. All right, K sub T. For this chart, what do we need? Okay, we need to know the ratio of the diameters. All right, and so capital D over lowercase d is 0.6 inches over 0.5 inches. Okay, and what's that? (1.2). All right, then we need to know the radius value so that we can look at the bottom of this chart. Our radius value is 0.0875 inches. Okay, so that tells me then that R over D, 0.0875 inches over, and of course this is for lowercase d, so that would be 0.5 inches. And that gives me 0.175. Okay, so that tells me here, the 1.2 tells me I'm on this curve. And then I need to read at 0.175. That's actually this line right here. Okay, and that tells me that I read up to right there and across to here. And what's my value for K sub T? 1.2. Yes, sir. Okay, let me hear some thoughts. The question is, what do you do if you end up with a capital D over lowercase d value that does not put you directly on one of these lines? What are your thoughts? Okay, one way you can do it is eyeball it, right? You can look at it and say, am I closer to one or am I closer to the other? And you can get a reasonably close guess based on that. Is there a better way that you might be able to do it? Can you interpolate? That's a good question. Can you interpolate? Well, why not? Yeah, so what you could do if you're between two curves, for instance, let's say that you drew a line up like this, and you figure out the value here, and you figure out the value here, right? You know what the d over d values are for those two locations, and you have a d over d value that you're actually trying to get, and so there's no reason you couldn't linearly interpolate between those 2 points. Right? You would need to read 2 different points. You need to read one on the curve that's below the value that you actually have and the one that's above the value that you actually have, and then do linear interpolation based on the value you actually have to figure out where along between those two values you really are. Okay? This is something that in your homework problems I sometimes have you do. Okay? It's not by accident. I want you to know how to be able to do that. So it's in some of your homework problems to be able to interpolate between two curves like that. Having said that, that is not something that I generally put on your exams, because I could have you spend a bunch of time doing that, but time is very precious when we're in the middle of an exam. So I generally will make these on purpose. I will make them a significantly good bit easier by having them show up directly on one of those curves. All right, does that sound good? All right, so now we have K sub t. What do we do with that? Okay, K sub t is 1.2. What we need to know is what's K sub f. To get K sub f, what do we need? Well, there's a whole process, and I showed you how to do it with the chart last time. I'm going to go back to doing it with the equation this time, and one of the reasons for that is that there is actually a different equation for your Neuber constant when you are dealing with shear rather than with a normal orientation of stress. Okay? And the equation that we're going to look to is equation 635b. Okay, equation 635b says that the square root of a, and that's the Neuber constant again, that's going to be equal to 0.19 minus 2.51 times 10 to the minus third. And this is times S sub ut plus 1.35 times 10 to the minus 5 times S sub ut squared. And then minus 2.67 times 10 to the minus 8 S sub ut cubed. And what we do is we take our ultimate strength value. You got a question?
Yeah, I was thinking that what if we have both bending, axial, and torsion at the same time?
Goodness.
How do we do this?
So the question is, what happens if you have combined loading? What if you have a part that has both bending and torsion and axial and maybe any combination of several forms of loading? We actually have an entire lecture dedicated to that possibility coming up in short order. So I don't think it's next lecture, I think it's the one after that where we do that. There's also a section in the book that's dedicated to what you do in that situation where you have combined loading. So we will get to that. It is something we have some techniques of dealing with that situation as well, but for right now, we're doing sort of one at a time. All right, so let's see. We're going to plug into this equation everywhere we see S sub ut. Okay. Remember, it is expecting you to plug in values that are in KSI, right? So you don't plug in KSI, you just plug in a number that is in KSI, right? So our number for S sub ut is 130 KSI, and so we're going to plug just 130 into this equation, and what we get out is a square root of a that is 0.033. And remember, what kind of units come out of that? Square root of inches. All right, so there's my Neuber constant. How do I find Q? Q, again, remember, is your notch sensitivity. Okay. What we do for Q, if you actually look up here, Q is equal to 1 over 1 plus square root of A. Okay, the square root of A being 0.033 square root of inches over, what do we put in the denominator there? Square root of the radius value, and the radius value is 0.0875. Okay, and I'm actually going to put a subscript on here. I'm going to call this Q sub shear. Okay, that's the notation they use in the book when we are dealing with this Q. And the reason it's different, right, is because we had a different equation for that Nuber constant. That's kind of where that difference arises from. Yes, sir? Because we are not given equations that work with a unit that would be in the SI system, what you would have to do, given only this book as your reference, what you would have to do is convert first into KSI, and then insert that number into the equation. You would get out square root of inches, and then you might have to convert square root of inches to a square root of whatever units you're using, you know, meters, millimeters, depending on what value your square root of r is going to be, and those should probably be consistent, right? So, yeah, anyway, that is not to say that reference materials don't exist somewhere that might give this to you, give these equations to you that are suitable more for the SI system, but, you know, that's how we have it. So if we're going to do an SI problem, we got to convert back and forth. All right, so there's my Q sub shear, and if I plug in those values and evaluate it, I get 0.899. So then I plug that into an equation to find K sub Fs. The little s on there means for shear. And this is going to be 1 plus Q sub shear times K sub Ts. And that's, by the way, another thing that, you know, they a lot of times, if it's a shearing orientation, they'll call that K sub Ts. It doesn't really matter, but that's, you know, I want you to know why they're using notation of a certain variety. So we plug in 1.2. All right. And what else do we have there? The rest of that equation is -1. And when we plug those values in, we get 1.18. All right, good so far. So now we have our stress concentration. Now we need to deal with how do we find our maximum and minimum stresses. Okay, so to do that, we need to deal with the idea that what we are given is basically a certain amount of angular displacement. We can, or at least that's what we will easily be able to come up with. Okay, so we'll start with the minimum. Okay, we can use an equation theta is equal to TL over JG. Okay, and from this equation we actually happen to know theta, right? Theta is 12 degrees, and this is at the minimum, right? So it ranges from being 12 degrees to a little bit more than 12 degrees when it rolls over one of these bumps. Okay? Angle of twist. Right. In order for this to move up by 12 degrees, it has to twist that shaft by 12 degrees. Okay? So I'll plug this in here as 12 degrees. And this is going to be equal to T, and this is actually T min times L. What's L? Okay, it's the length of this torsion rod, which is 18 inches, over JG. J is pi over 32 times d to the 4th. And we're just going to estimate That D, we're going to sort of ignore the fact that the ends get a little bit bigger. That's not uncommon to do that. Probably makes a very small amount of difference. Okay, and it's that to the fourth. Then what? Okay, modulus of rigidity for this material. The modulus of rigidity for steel can be looked up. I believe it's in table A5 at the end of the book, and it is 11.5 times 10 to the 6th psi. Okay. Now, before I start plugging and chugging here, there's one thing I should probably take a look at. Okay. If you think about the TL over JG, it is set up to give you an angle that is in radians, and we're putting an angle in degrees right here. So what we should probably do with that is multiply by pi over 180 degrees. Okay, and that puts us in radians so that we are consistent with how it would come out of the other equation over there. All right, so plugging and chugging now, we get that T min, and this is, remember, this is without a stress concentration or anything thought of just yet. Of course, we haven't done stress yet, but this is a torque. This is the minimum torque that it has to carry. And that ends up being 821 inch-pounds. All right, what do we do for maximum? Okay, it'll be 12 degrees plus a little bit more. What's the best way for us to come up with what that little bit more might be? Okay, you could kind of do it that way where you found a little hypotenuse of a little triangle right there. I'll say that for the size of the displacement right here, 1/8 of an inch over a length of 2.5 inches, I feel comfortable using basically just the definition of radians. Right? Remember, radians is arc length over radius. Right? That's how you'd measure a radian, is arc length over radius. And what we're basically trying to get there is more or less an angle based on a change in what we could kind of think of as arc length over the radius, which is just the length of the arm. Okay? So what I would do for this next part is say we are going to have 12 degrees times pi over 180 plus, right, we will have again the ratio of arc length over radius. And arc length, we can just use 1/8 of an inch, which is 0.125 inches, over the radius, which is 2.5 inches. And that's a good enough estimate for how much angle change that we have right there. Okay? Let me just comment to make sure that there's a reason why I can do that. The reason why I can do that is my presumption is that this arm is basically horizontal in its neutral position or in its starting position. And because it's basically horizontal, the amount of arc length is pretty close to just the amount of height change. Okay? Yes, sir? Everything's an estimate. Yeah, it's an estimate. It's going to be very, very, very close to what you would get if you tried to actually work out the geometry.
So what are we doing with this? You converted 12 to radians, and then you divided 0.125 by 2.5 and added that to it. What is this exactly?
So this is your sort of the pre-displacement, the 12 times pi over 180. That's how much displacement we had at the very beginning, yes, right? When it rolls over this 1/8 inch tall block, we get a little bit more angle, so that where that would be kind of like this arm moving up a little bit, right? So that it lets the roller go over the top of it, right? And that little bit of angle right there, how much that changes in angle is what that second term is giving us. Okay, so this is going to be equal to our maximum torque that it experiences multiplied by 18 inches divided by pi over 32 times 0.5 inches to the fourth times 11.5 times 10 to the sixth psi. So our maximum torque then becomes 1,017 inch-pounds. Okay, so what we've done now is we've converted a certain amount of displacement into a certain amount of torque based on what we know about the shaft. What's next? Okay, so we find shearing stresses. Okay, for the shearing stresses, our maximum shearing stress, okay, and again, think of this kind of like a max, right? This is, we're going to also put in our stress concentration value. So this is sort of overall maximum. We're not even going to even really talk about the nominal stresses really here, but understand that we're multiplying by a stress concentration factor so that it's not nominal, it's actually the real stresses, including an accounting for the stress concentration. All right, so we have our maximum torque there of 1,017 inch-pounds. Okay, the formula that we're using here is Tc over J. C is the radius of the shaft, and that is going to be half an inch over 2, correct? All right, and then in the denominator, we have J, pi over 32 times 0.5 inches to the fourth. Okay, I need to multiply all of this by my K sub Fs value, and my K sub Fs value from down here was 1.18. Okay, and so what I get there is 48.9 KSI. And that's a shearing stress. That's going to become important here in just a few minutes. All right, what's my minimum stress? And again, this is accounting for stress concentration. Same thing, only thing I change is I go down to my minimum torque of 821. Okay, we have the same radius. We have pi over 32 times the diameter to the fourth, and we have the same fatigue stress concentration factor. All right, and when we plug all of those in, I get 39.5 KSI. All righty, then what? Okay, tell you what, while we're here talking about these stresses, what we need to plug into our failure criteria are not max and min stresses. We need to plug in mid-range and alternating stresses. So what we should do probably at this point is go ahead and find mid-range and alternating stress values that are associated with these maxes and mins. So I'll say tau sub m is going to be equal to 48.9 KSI plus 39.5 KSI over 2. Okay, and I get a 44.2 KSI for the mid-range. For the alternating component, it's similar, but we take a difference instead, 48.9 KSI minus 39.5 KSI over 2. And for that, I get 4.7 KSI.
What exactly is tau sub A?
This is your alternating component of stress. So what you think about here is that halfway through the range of motion of that lever, the stress in the shaft is going to be that mid-range stress. But the stress is then going to change off of that level by positive 4.7 KSI and negative 4.7 KSI off of that middle position.
Yes, sir.
All right? So there's our mid-range and alternating stresses, and we're going to remember those for when we get into finding factors of safety using our failure criteria. Okay? But we need one other factor as well. What's the other factor we need? SE. We need our fully corrected endurance limit. Okay? Which means we need to put in some Marin factors. All right? So we'll start with our surface factor, K sub A. Okay? What's our surface like? It says it's a machined surface, right? So we go and we look up that textual description in table 6.2. It gives us 2.7 for the the coefficient out here. We then multiply that by S sub UT, which is 130. Again, we'll strip those units because this is a kind of experimentally based curve fit sort of oriented equation. And we put in an exponent of negative 0.265. Okay, and evaluating that, we get 0.743. All right, what about K sub B? All right, so for K sub B, we have basically a similar kind of stress distribution as you would have if you had rotating bending. Like, think about the amount of area that reaches 90% or higher of the most maximum stress. What shape is it? It's kind of a donut shape, right? Which is the same thing you get in rotating bending. So what we can do is directly use the equation that we have for the size effect, K sub B, for this torsional case, because that shape of our most highly stressed material is the same as the shape of the most highly stressed material you would have in a rotating bending test. All right? So we're going to put in, our D that we have is between 0.11 and 2 inches. So we're going to use the top line of equation 620. And KB ends up being, our diameter is 0.5 inches. Okay, you divide that by 0.3. And again, I'm going to, since it's expecting it in inches, right, we don't want to leave the inches in there, especially if you're using something like MathCAD, it's going to wreak havoc on it. All right, so we put that in there. We then have an exponent of negative 0.107. And when we compute this, we get 0.947. Okay. What's next? K sub C. K sub C is the loading factor, right? And all you got to do on this one is identify what kind of loading it's in. And we are in torsion. And it recommends what for torsion? 0.59. I want to make a comment here at this point. Mostly what that does is it converts your endurance limit value from being a stress that is a normal orientation, or a strength that is a normal orientation strength, to being a shearing orientation strength. Like the biggest component of that correction factor right there is the 0.577 that we would have had finding the shearing strength from the normal strength using our distortion energy theory. Right? It's no accident that those numbers are so close to each other. Okay? So that what I'm going to say here is that this converts what we would have called S sub E to S sub SE. That's a, yeah, I think they actually have that maybe a couple places in the book, where this is sort of the endurance strength in a shearing orientation. Okay, so this makes it appropriate to compare shearing stresses against the value that we get out of this endurance strength. And that's going to be important here in just a few minutes. All right, what's next? K sub D. Are we given any information here that this is at elevated temperatures? Okay, don't let yourself be tricked. I mean, I've had many students over the years look at information that might be given about a particular type of material. Okay, if you see quenched and tempered at 1200 degrees Fahrenheit, that is not information about how it is operating. That's information about how the material was processed. Okay, so that's not operating conditions. That's actually how that material was tempered. Okay, so don't let that confuse you. So we basically can use K sub D equal to 1 because we are not given any information about anything special with respect to temperature. All right, so then what? K sub E. K sub E is the reliability factor. At 90% reliability, K sub E is 0.897. Okay, and that's just looked up out of table 6.5. All right, those are all of our Marin factors. Okay, so we're going to use all these Marin factors to come up with, okay, I'm actually going to label this S sub SE. And I'm doing that because of that factor of 0.59. Okay, I'm making a very specific note to myself that this is a strength value that is appropriate to compare against shearing stresses, not normal stresses. Okay. So we put in here 0.743, 0.947, 0.59, 0.897, and then what else? Half of 130 KSI. All right, so S sub SE becomes 24.2 KSI.
Dr. Swalwell?
Yes, sir.
You got K sub C. What did you do to convert
that is the factor. Once you've applied a K sub C of 0.59 for that idea of going to torsion, I'm basically pointing out that the main reason why that number is so different than all the rest of them is that the main thing that number is doing is converting this strength value from being one that is appropriate to compare against normal stresses and converting it to something that's appropriate to compare against shearing stresses. Okay? All right. We ready to do this? I think we've got most of our numbers. Let's flip over and I'll show you a page in the book. Okay, we'll start on page 315, table 6-7. So to find our Gerber factor of safety, all right, N sub F, and I'll just label down here, this is for Gerber. It is going to be equal to, and there's a big long equation right here, it says 1/2 S sub ut over sigma m, this is squared, multiplied by sigma a over S sub e, this gets multiplied by -1 plus square root of 1 plus 2 times sigma m, again that's mid-range stress, times S sub e. All this in the parentheses is squared, and this is divided by S sub ut times alternating stress. Okay, so if you're wondering where that is, that comes out of table 6-7. All right, one of the things I want to point out here is that this equation is set up entirely for normal orientation stress. Okay, that's what this equation is set up to do right now. We need to convert this into an equation that's appropriate for shearing. Okay, we've actually done most of it. We're only lacking one little thing. Okay, the thing that we lack is we don't, I'll tell you what, let me actually go ahead and write it. 1/2, this is what we want it to become. We want this to be 1/2 of an ultimate strength in shear, not an ultimate strength in a normal orientation for the numerator of this first piece. Let's give that a name. Okay, they actually call that in the book S sub SU. Okay, this is an ultimate strength in a shearing orientation over tau sub m. Up here we're going to have tau sub A over S sub SE. We already found that part, so we're good as far as our endurance limit in the shearing orientation. We have that number already. This gets multiplied by -1 plus the square root of 1 plus 2 times tau sub m times, this is S sub SE, over S sub SU times tau sub A. Yes. Thank you. It's the same exact equation. All we're doing is we're going through and converting all of our strengths to being strengths in a shearing orientation and all of our stresses to be stresses in a shearing orientation. All right, but that means we actually need to calculate for S sub SU. That's the one thing we don't have yet. Okay, well here's how that's done. S sub SU, it says here in section, find it here real quick. In section 613, equation 654, it says S sub SU can be estimated as 0.67 times S sub UT. This is on page 325. This is equation 654. So S sub SU then for us is going to be equal to 0.67 times 130 KSI. All right, and that gives us 87.1 KSI. All right, so now what we want to do is start plugging it in. So our Gerber factor of safety, we plug in S sub SU up here, 87.1 KSI. We plug in tau sub M. Got to go way down here. Tau sub M was 44.2 KSI. All that's squared. Then our next term, we have tau sub A. Tau sub A, our alternating component of stress, was 4.7 KSI. And we divide that by the endurance limit in shear, which we had just down here for 24.2 KSI. Multiply all this by -1 plus the square root of 1 plus, here we will have 2 times, this was 44.2 KSI, times S sub SE, which was 24.2 KSI. S sub SU is 87.1 KSI, and tau sub A was 4.7 KSI. And all of this stuff was squared. Tap a little bit on your calculator, and out of this comes 1.629. Yes, factors of safety are unitless. Okay. Do we feel safe? I mean, right now we do, right? That's a factor of safety of 1.629 for infinite life. It's awesome. All right. What's next? Okay, we want to do ASME elliptic. We can actually go back to a table that's right near table 6.7, table 6.8. And we're given a fatigue factor of safety for ASME elliptic. It's actually a pretty good bit more simple. Okay. It says, and I tell you what, I'm just going to convert it on the fly over to being for shear, right? It says we have the square root of 1 over. Okay, the first term we have down there in the denominator is alternating stress over endurance limit Okay, I'm going to change that to, in the shearing orientation, tau sub A over S sub SE. Okay. Next we have mid-range stress, which I'm going to make in the shearing orientation as well. And this is divided by S sub SY. Ah. Now that creates another question. What do I use for S sub SY? Okay, this is, I'll label it on here. This is our yielding strength in shear. How do I evaluate that? Yeah, I can use the distortion energy criteria that we learned last chapter, and we can multiply by 0.577 to get S sub SY. Okay, this is based on our distortion energy criteria we had in Chapter 5. Okay. The other way you can state this is S sub Y over the square root of 3. Okay, this is based on that elliptical shape that we had for our distortion energy criteria, the whole idea of von Mises stress, all of that stuff that we had. We came up with an estimation that we could use to find yielding strength in a shearing orientation if you knew yielding strength in a normal orientation. Okay, and so for us, then, that equals 0.577 times, what was our yielding strength? 80 KSI. And this gives us 46.16 KSI. Okay, so now I can plug these into this equation with numbers. I have 1 over tau sub A is 4.7 KSI. S sub SE is 24.2 KSI. Those are squared. I add to this tau sub M. All right, tau sub M was way down here, 44.2 KSI. Over S sub SY, which we just found, 46.16 KSI. All right. And that becomes 1.024. That's for ASME Elliptic. Do you feel safe? You feel like it might fail before we have infinite number of cycles? I don't know, we're at least getting in that range where we're starting to feel a little bit less comfortable. Okay? Well, how about this? The other thing we're supposed to do is calculate a factor of safety against first cycle yielding. How do we do that? Okay. The yielding strength for first cycle yielding? What we want to do is take our strength value divided by our stress value. The strength value is that one we just found, 46.16 KSI. And what's our maximum shearing stress that we induce in this shaft? Okay. 40, what was it again? Okay. To remind ourselves where that came from, it came from down here, 48.9 KSI. And if we plug these in, we find out what? This tells us that we are likely to have first cycle yielding. All right? If we have first cycle yielding, what does that mean as a consequence? Okay? It might mean we don't end up with the same amount of sort of pre-tension. Right? If it begins to yield a little bit, then if we completely unloaded it at all, it's possible that this arm could actually drop down to a height that is not quite as low as it did originally, right? So that might not be desirable, okay? So we have to kind of keep this in mind. All right, this is first cycle yielding. This one doesn't really have a number. This is that the whole idea of factor of safety is always basically strength over stress. Like how much does it take to break it divided by how much are you actually applying, right? And in this case, for first cycle yielding, we are directly comparing how much shearing stress, that's the 48.9, we're comparing that against the shearing strength, which is 46.16. All right, what I want to do is show you here, specifically for this problem, I did a plot that shows you the different failure criteria. Okay? And you get to visualize each of these things that we just found. This is our point right here. This is the load line, is basically a line that starts at 0 and goes out to that point right there. Okay? We didn't evaluate our, we didn't evaluate the black line right there. That's the Goodman criteria, right? But you notice there that both the Goodman criteria and the Gerber criteria, neither of those are going to give you a bad factor of safety. Both of those say, looks like you're fine, right? It's only when you look at the Langer criteria, which is yielding, that's first cycle yielding, you realize, oh, it looks like it'll yield in the first cycle. And the other thing that you will notice here, and you know it's really illustrated well, is that the ASME elliptic criteria would not predict that you have a problem necessarily, and yet it looks like you would have some first cycle yielding for this. So this is a, and by the way, this was not by accident. I picked the values carefully for this problem to put you right there so that you get to see an example where the point, the loading point that we have on the load line actually, you know, creates a bit of a dilemma for you, right? ASME elliptic says you're okay. Langer line says you're not. Yes, sir.
We would judge whether it's okay or not, whether it's below the load line.
Anytime the loading point, which is this point right here, if that point lies to the inside of your failure curves, right, your interpretation of that is that the further to the inside of these curves that point lies, the better off you are, right? When it starts reaching out to being close to these lines, you start getting worried, right?
Like if it were like inside that little triangle there,
Uh-huh.
if it were inside that, we'd be safe.
Like if you were back here.
No, sir. The little space right below your red dot.
Like down here?
Yes, sir. If you were in that, you'd be okay.
you're right at that point that I drew right there. That would also predict that you would yield by a little bit. Like it basically, you're right outside of the range where you would have yielded. So basically think of this green line, and anything like that goes this way from the green line is unsafe. You have factors of safety lower than 1 for your Langer criteria, which is the first cycle yielding criteria, if you're to that side of the line, right?
So we can't trust the ASME.
The point here is that ASME doesn't do a perfect job of predicting whether you will have first cycle yielding. Okay? Now, is it any good at all? Okay. What if you specified, you say, I'm going to do these fatigue designs, and I'm going to make sure that my factors of safety are never any lower than 1.5. Okay. Now you kind of feel okay, because even if you wind up with a load line that's in your worst case scenario, like the worst case scenario might be something that would be right in here somewhere, right, where you have the furthest amount of distance between the Langer criteria and the ASME elliptic criteria. If you're doing a factor safety 1.5, it means your point that you're loading might be back here, right? Or maybe not quite that far back, but like it might be back something like this, in which case, you know, you're probably still safe. All right, so there are some examples of where using the ASME elliptic criterion all by itself might be kind of okay. All right. Questions or comments?
So why don't you just use the Langer line always for first cycle yielding?
That's actually what the book recommends. Okay? It actually recommends that for any of these fatigue failure criteria that you use, that you also evaluate a factor of safety against first cycle yielding. All right? And I'll echo that. That is a good idea to do that. Okay? But you know, having the ASME elliptic criterion as one sort of continuous and smooth criteria that at least does something to account for the possibility of first cycle yielding, you know, just, it's good to know that that's out there. All right. If there are no more questions, then I will see you guys on Friday. Have a good couple of days till then.